Hello friends, today I will talk about binary search algorithm solution with recursion. There are various search algorithms and binary search is one of them, and it's a popular search algorithm. Before I start about its recursive solution, let me tell you a few words about how binary search works. Now, I'm going to use a sample sequence for that. Let's say that we have 1, 3, 4. Let me delete this part. 5, 17, 18, 31, and 33. This is a sample sequence. Let's say that we are keeping this sequence in an array. We can call it A, assume that the name of this array is A. And in this array, we have these numbers. So this is the first number, which means A0 is here. A1, A2, A3, A4, A5, 6, and 7. Okay. Now, assume that we are searching for a number here, and it is, let's say that it is 17. I'm calling it search key. Okay, I'm calling it search key, and we will look if this number is in this sequence or not. Okay, how binary search works? First of all, it starts with this. It says that this is the low point, this is the high point. Okay, and low is 0 and high is 7. Low and high keeps index numbers of the first and last element that it is going to search. And in this first step, it finds midpoint of this sequence. It will find the midpoint of this sequence. Okay, and what is it? It is low plus high over 2. And according to sample sequence, we can say that the first mid is 0.7 over 2, which is equal to 3.5. Actually, mid will be an index also, and we don't have this type of index, so we need to remove fractional part. Therefore, here division is being as integer division. So when we make integer division, it removes the fractional part, and it only gets the integer part. So we can say that mid is equal to 3. We will use this formula for calculating mid, because this is not the only point that we are finding mid. We will continue to find mid until we are sure that the number is not in the sequence or the number is in sequence. And we'll use this formula in every step. This is our first step, and we found that mid is 3. Okay, mid is 3 means mid includes index number of the mid element in the array. Actually, 3.5 is the mid, but we don't have any element with a fractional part in, so we did integer division and we assume that this is the mid element of this array. So that's why mid is equal to 3. Anyway, okay, then if mid is 3, mid is 3, then in the first step, I'm checking if the search key is equal to the mid element. Is 17 equal to 5? True or false? It's not equal to 5. Actually, if we were looking for 5, 5 would be equal to 5. And then we can say that we found the element in this sequence and finish the algorithm, terminate the algorithm. But now we are looking for 17. So 17 is not equal to 5. Okay, what happens then? Friends, let me tell you an important point here. If you are using binary search, okay, your sequence must be ordered. Okay, this is very important because if it's ordered, binary search will not work. Okay, and if we look to our sequence, the numbers are in order. They are in ascending order. Okay, this is very important. If you want to apply binary search algorithm to any sequence, that sequence must be ordered. Okay, this is the rule of applying binary search. Okay, then in this situation, when we look 17 and we see that 17 is not equal to 5, we are comparing it. If 17 is less than 5, we will consider the left part. If 17 is greater than 5, we will consider the right part. And when we look here, 17 is greater than 5. Since 17 is greater than 5, then I am sure that the number that I'm looking for, it will be, if it exists in the sequence, it will be in this part. Isn't it? So I do not need to check this part. Okay, I don't need to compare my search key with A0, A1, and A2 because I found the midpoint and I see that the search key that I'm looking for is not equal to this element and it is greater than this element. So I need to check this part. So I am, here by using binary search, I am earning time. I am decreasing the computation time. Okay, in this situation, I will look to this side. So how I can do that? In the next step, if if my search key is greater than mid, so I need to move low. To here. Okay, so how I can do that? I will say that low is equal to mid plus 1. So when I do that, low will be moved here. And now, low will point here. High is still points here. Okay? Okay. Then in the next step, this is our second step according to the sample, I will calculate mid again. So what is mid? Mid is equal to high, it is 7, plus low, it is 4, over 2, which is equal to 5. Don't miss a point here. This is integer division, okay? So that's why it is 5. Okay, if mid is equal to 5, then mid will point here. Okay, now I'm looking if my search key is equal to the element at midpoint. Okay, and is 17 equal to 18? Yes or no? If I was looking for 18, the answer would be yes. But I'm looking for 17, so 18 is not equal to 17. Therefore, I'm going to compare 17 with 18. Okay, if 17 is less than 18, we'll look to this part. If 17 is greater than 18, then we will look to this part. And in this situation, 17 is less than 18. 17 is less than 18. Therefore, we need to consider this part. and we do not need to look this part. Okay, we do not need to look this part. Okay, then what happens if we are going to consider this part? Then I need to move high from here to here. So what I say, high is equal to mid minus 1. Okay, and high will point this position. Okay, and here I will find mid, because I'm going to check this part. Mid is equal to low plus high over 2. It is 4 plus 4 over 2, and the result is 4. So mid will also point the same element. And I am checking if my search key is equal to the element pointed by mid. 17 is 17 equal to 17? Yes. When we found that it is yes, then we can say that yes, the number we are looking for is in this list, and it is found on the midpoint. Mid is equal to 4, and this number 17 is on index 4. Okay, which means it is found on A4. This is what we found. And as you see, we searched this array by comparing only 3 numbers. We compared with 5, we compared with 18, and we compared with 17. So we didn't compare with these numbers, and we didn't compare with these numbers. So we decreased the computation time while we are searching a value in this array. Okay, here if we were looking for another number other than 17, this point is also important because we should also spare a part in this algorithm for this type of condition. We have this value in the sequence. If we do not have this value in this sequence, for example, if we were looking for 16 instead of 17, what would happen? Actually, we would come until this point and we would say that 16 is not equal to 17. 16 is not equal to 17. So we need to, move high. Actually, we need to compare 16 with 17, and 16 is less than 17. So if it is less than 17, then we need to, you know, we need to check this part. But in this part, we do not have any value. Okay. So how it happens? We are continuing to apply the regular step here. We say that high is equal to, we need to move high to here. Okay, because 16 is less than 17. So if it is less than, we are decreasing high. We are saying high is equal to mid minus 1. Okay. If it is greater, we are saying low is equal to mid plus 1. That's the policy I applied. We apply. And here we are saying that high is equal to mid minus 1. Okay. And in this step, let me clear this part. In this step, what happens? High will be moved to here. High will be moved to here. So high is equal to mid minus 1. So it will be 3. Okay. And low will stay at the same place. Okay. And so what happens? High Let me clear this part. Okay. High will be here. Okay. And low still on the same position. And here it is very important. When you look to this, we don't need to calculate mid. When we look to this point, we see that high is less than low. This condition happened. Okay? This condition happened. Actually, we need to look, we need to check if 16 is existed here or not, but we don't have any element here. And when we apply our step, high will be 3. So this condition will happen. So when this condition is happen, we don't need to continue to calculate mid and make new comparisons, because when this condition happens, we are sure that the number is not in the sequence, in this list, let's say, in the array, let's say, okay, in the array, okay, is not in the array. So this number 16 is not in the array. So when we have this condition, we can terminate our algorithm, okay, and we can say that the number is not found. So we have 2 points that we can terminate. The first one, we found the number. So until we find the number, always high is greater than low, okay? And the number is on the mid. But if the number is not in the list, so we are reaching this condition, okay? This is the idea how binary search algorithm works. Okay, in this situation, let me write the algorithm for you. According to these explanations, how we are writing our algorithm. First of all, I need to consider our termination point. And the first one is if, let me write it here, if low is greater than high, or high is less than low, it's the same thing. We are returning -1. So it means that the number is not in the list. Okay, if this condition is not happen, so I can find the mid and check if the number is there or not. So I'm saying mid is equal to low plus high over 2. And if the search key is equal to the element at the midpoint or not. Here I used A, but assume that our array name is A, so that's why I used A here, okay? And if they are equal to, if the search key and the element at midpoint are equal to each other, then we can say that return mid. So why I'm returning mid? Because mid includes the index number of the search key, and I am returning mid to the caller. So caller, if the caller gets number other than -1, so it can understand that the number is found on that index. So that index is mid. Okay, okay. Then if they are not equal to, so I need to, make comparison between search key and the element at the midpoint. Okay, so I'm saying if search key is less than the element at midpoint, then what happens? Oops, sorry. Okay, what happens? I need to search for search key in a low to a mid -1. So what happens here? If search key is less than the element pointed by mid, then we are decreasing high by 1. This point is high actually. Decrease the high by the high will be equal to mid -1. So the algorithm will make new search between low and new high. Okay, if this is not if search key is greater than a mid, then in the else part I will search for search key in a mid plus 1, because it's this means that my search key can be on the right side of the mid. Then a mid plus 1 to a high, and the search will happen between new low and high. Okay, this is the algorithm. So here let me write C code of this algorithm, so it will be more clear for you, I think, because we are working with a recursive solution. And let me write its recursive function here, and this is our algorithm. Let me write its C code here, C code. And first of all, let me define my function. I'm saying integer. Let's say that binary search. Okay. I need some arguments. The first one should be my array, of course. So I am saying a, and I need a value that I'm looking for. So let's say that it's my search key. I need low and I need high. Okay. Okay. And this is the definition of my function. And I said integer here because I'm going to get a value back. So if I get -1, I will understand that the number that I'm looking for is not in the array. If I get a number other than -1, so I will understand that it is found in the array and I'm getting its index. Okay, then here what I am doing, I need to declare integer mid. And first of all, I'm going to check if low is greater than high. If this happens, I'm directly returning -1. And then I will calculate mid, low plus high over 2. So when I say it, the sum of two integers will be produce integer value, and if you divide integer to integer, result will be integer division. So mid will be integer. Okay, and if there is any fractional part, it will be removed automatically by the compiler. Then if search key is equal to a mid, then I can say that I found the number. So I'm returning mid. And here I need two conditions here. Then the other one is if it comes here, then this means that search key is not equal to the element at midpoint. And then I'm checking search key, if search key is less than a mid. If it is less than a mid, then here I am saying that return binary search. I'm calling the function again with the array A, with the search key, with the low and mid -1. Okay, so what happens here? What happens here? I am calling binary search function again. This is recursive call with the array A, with the search key, with the same low, but with new high. I told you if my search key is less than the value pointed by mid, so we need to move high to the left part, to the left side of mid. So high is equal to mid -1, and we need to search the left part of mid with the current low and new high. So that's what I'm doing here. And in the else part, I will say return binary search a search key. Now, if search key is not less than a mid, so I need to move low to the right side of mid. Therefore, here new low is mid plus 1, and I will use current high. Okay, and this is recursive function of let's say binary search. Okay, starts here, ends here. Okay, let me show you one more thing. Let's say that we want to call this function in main. We want to call this function in main. So how we can call this function in main? Let me write it here. Let's say that we are in main or in another function, let's say, and we want to call this binary search recursive function. So you can say that, for example, result is equal to binary search. You are writing your array name here, doesn't matter what it is. For example, array, and we are looking for x, and we will search it between index 0 and index n minus 1, for example. And when we call it, it will return as a value. So if result is equal to -1, it means that it is found. Okay, it is found. Otherwise, it is found. I can say printf found. Okay, otherwise we can say that not found. I'm sorry, this is not found when it is -1, not found. And if it is not -1, we can say that found at index this. What is that index? Result. Okay, because binary search will return me a value. If it is not one, if it is not found, it's -1. If it is found, it will be the index of the location that it found the number. So I can say that found at index result. And this is how we can call, or how we can use, let's say, how we can use recursive binary search function in our code. And that's all. Have a nice day.